In this tutorial, we will look at Berger's equation in 1D. It's basically also called diffusion advection because we have both advection and diffusion terms here. And we will use the same code that we developed for the 1D case, advection case, and add another diffusion term to it. And here is the numerical implementation. We add this second derivative into our model. So going back here to the advection 1D, we save it as the advection diffusion or diffusion advection. Both are fine. And everything else stays the same, except now we have another parameter here. We have k parameter, which is the diffusivity or the diffusion factor, and then we have to initialize it as well. So let's say k is equal to 1 everywhere. So, and then right here we need a diffusion term. And let's call it d, and that is equal to the diffusion factor times the second order derivative and what do we put here? Well, that's Cn on the left minus 2 times Cn at the node plus Cn on in the right side, and make sure it's capital Cn, and this should be multiplied. Okay, so that's the diffusion term. Now we have to add this term here, plus d. Now one thing you can do here is remove the negative sign from here and add the negative sign here so that you don't have to carry negative sign in the advection, because technically this is the advection term, not the minus of it. Okay, because the advection term appears on the right side. Oh, and let's update the equation as well. Cxx plus, and now as we can see that we will have to access the next value from the current value, so we cannot be at nx, because when we reach nx it's going to try to access nx plus 1, which doesn't exist. So we can only run it to 1 before the last value. And so if we're running it up to this point, we don't know what the last value is, so we have to put a boundary condition for the last value. And in our case, we can assume that we can consider it to be a Neumann boundary condition, and that would set the current value, the value at the last node, to be the value at the previous node. And then we can keep the periodic boundary condition as well, so that the value here kind of gets passed on to the other side. And that's pretty much it. We can run this code and see how it behaves, and it looks like it's blowing up. When you see these lines, that means the values are really large. And the way to fix this is that we have to reduce the CFL value, because the CFL value is very large, which is making the DT value very large. So let's try 0.5 for the CFL value and rerun it, and it's still blowing up. I'm going to reduce the time. It's running for 15 seconds. I'm going to reduce the time from 15 to 5 seconds so that we can see the results a little bit faster. Let's reduce the CFL value further, and it looks like it has started to work fine. And because the starting concentration was 1, and it kind of diffuses very quickly, we can increase this to or we can change the range of our y-axis to have a better view of this. So let's change the range from 0 to 0.1. 0 to 0.1. And now you can see that we have convection and diffusion happening at the same time, and the periodic boundary condition is working too. So at the end, this node kind of start contributing to the first node. So this is how you can implement the Burger's equation or advection diffusion equation in 1D. We can also test one other thing. Here, U values are same everywhere. So let's say these values are actually 0.1, 0.5, and we set the value for part of it, maybe from 4 to 7 to a 1 value. So if nx is equal to 20, then this is about 8, and then this is about 14. So 8 to 14, we set it up to 1. So we say here u 8 to 14 is equal to 1. So what we're saying is that the speeds here are 0.5, and then from here to here the speed is 1, and then it goes back to 0.5. So let's see how does this behave. So when it hits 0.4, it's going to speed up a little bit, and then it slows down again. So it's not very clear here. So we can maybe move it a little bit ahead or reduce it. So let's run it from maybe 4 to 6 and rerun this.